Okay, so it's our pleasure to introduce Eva Halacheva from Northeastern University, and she will be speaking to us about perverse equivalences and cacti.
Thank you, Peter, for the introduction, and thank you very much to you and Jeremy for inviting me to speak at this conference. I realize the topic of my talk is a little bit more on the algebraic side than perhaps most of the talks at this conference, but there's definitely some Lie theory in there. Well, this is what I've been thinking about these days. So this is what's on my mind. So I hope you don't mind me speaking about this. So, so the title might sound a little bit mysterious, Perverse Equivalences in Cacti. I hope to shed some light on it throughout the talk. So in the next 24 minutes. So let me start with a little bit of an overview of where we're going with this project. And I should mention that this is a joint work with Ivan Losev, Tony Licata, and Oded Yacobi. Here's the overview before we get into a little bit more detail. So take a simply laced Kac-Moody Lie algebra G. And so here are some things you can build out of it. So I guess I'll use my mouse to point. So for instance, where do we start? We have the quantum group for G, and we can consider the quantum group representations. And from there, Lustig describes how to define, using a quantum group module, an action of the braid group for our Lie algebra G on that module. So there's this arrow going from quantum group modules to braid group actions. And furthermore, this arrow going down here is a construction originally due to Kashiwara, where given a quantum group module, by taking a certain limit as Q goes to 0, you can obtain a G crystal for the given representation. There's various models for them, combinatorial, geometric, and so on. And in work with Joel Kamnitzer, Lenya Rybnikov, and Alex Weeks, we've shown that for a given G crystal, you can define an action on that by a so-called cactus group defined for this Lie algebra G. So these downward arrows, we would like to think of them as the freezing arrows, or the Q goes to 0 limit of them. But in particular, we'd be interested in studying more this dashed arrow on the right. And we will do so by looking at a higher, more categorical or higher category version of this diagram. So there is a categorification of quantum group representations. So K0 here is taking the Grothendieck ring. And so this has been established by Chuang and Rouquier and Kovanov and Lauda, among others. So given such a categorical quantum group action, furthermore, work of Chuang, Rouquier, and Cautis and Kamnitzer shows that you can build certain perverse equivalences called Rickard complexes. And they satisfy, in fact, the braid group relations. And so from a categorical quantum group action, you can get to a categorical braid group action. And connecting this to the lower row, a work of Lauda and Vazirani shows us that also from a categorical quantum group action, you can get to a crystal on the for the Lie algebra, or the Kac-Moody Lie algebra. And so what we're interested in doing is studying a relation between categorical braid group actions and cactus group actions. So we would like to look at these Rickard complexes in more detail and understand how to get to a cactus group action from them. Okay, so that's my first slide, and that already took 5 minutes, but I don't have too many slides, so hopefully I'll be on time. So let's start with a little bit of a warm-up. So just considering the simplest, or one of the simplest Lie algebras, SL2. So we have the basis. Let's work over the complex numbers, E, F, and H. And this is acting on some integrable representation, so a graded vector space graded by the integers. And we have the linear maps E and F on the weight spaces. And they satisfy the relation that EF minus FE restricted to the nth weight space is n times the identity on that weight space. So this is the structure we'll be focusing on describing the categorical level for. So, and I won't be completely precise here just for the sake of clarity, but let me say, so then what is a categorical version of this? Well, we replace the vector space with, some people use an additive category. In this case, I'll use an abelian category because I want to think about derived categories of that a little bit later on. So we have an abelian category, which is made up of categories indexed by the integers, whose Grothendieck group is the weight space for our representation. And we'll have exact endofunctors of this category E and F, which restrict to the categories indexed by the integers in a natural way. And so this information so far gives us a weak SL2 categorification. So to make it a strong one, we're interested in also understanding precisely how to categorify this relation between E and F. And so for that, we'll need several natural transformations. So we'll take epsilon and eta to be the unit and co-unit of a junction. So we want our functors to be adjoint to each other. And we'll also consider certain natural transformations on E and E squared, which will help us to categorify this relation. So let me not list all of the things they have to satisfy, but in particular, one thing they give us is an isomorphism between these functors. So remember, the relation was EF minus FE is n times the identity. And here we've moved FE to the right. And so this is precisely that relation now in categorical form. And there's a certain isomorphism that we obtain using the natural transformations we saw on the previous slide. I won't get into details for this. And one other interesting condition is that the natural transformations X and T in particular give us an action of the nil-affine Hecke algebra on e to the n. So nil-affine Hecke algebra on n strands acting on e to the n. Okay, so this is a little bit of a warm-up with SL2. And so here's an example of its adjoint representation. So we have each of the weight spaces here replaced by certain category, and the raising and lowering operators are replaced by, in this case, induction and restriction functors. And these give us an honest SL2 categorification of this representation. And so I'll get even sketchier talking about the more general setting, but oops, oh, sorry, this is a little bit cut off at the bottom. But so more generally, if we're looking at a Kac-Moody Lie algebra G, we can think of its idempotent form instead, which is taking the universal enveloping algebra of G and adjoining a certain system of idempotents. And through doing that, this lends itself to thinking of it as a one category. And so then a natural way to categorify that is via two category, which has objects indexed by or labeled by the weight lattice for G. One morphisms are going to be the analogs of the raising and lowering operators. and the two morphisms. And there's a very nice graphical calculus for them, and I've stolen these pictures from Joel. So thank you for posting them on the archive. We have these two morphisms, and they have to satisfy certain relations. For instance, the KLR algebra relations for the upward pointing strands, and some further relations, which I won't get into in the moment. But so there is a notion of the categorification of the universal enveloping algebra or its idempotent form, and then a categorical representation is a two-functor from this two category to another appropriate two category. And we can also express this in the quantum setting. So I think this is still reasonably readable. So we have a certain category where there's also grading introduced, which categorifies the idempotent form for the quantum group. Okay, so let me then move on to given a categorical representation or a categorical the algebra action, let's talk about the Rickard complex, which we can get from that. And so for simplicity, again, I'm going to be talking about the non-quantum setting here. So consider the element S, again, going back to SL2, which is a lift of the non-trivial Weyl group element for SL2. We can express it in the following way as mentioned here, and this lives in the Lie group SL2. This expression can be quite unwieldy, but if we restrict it to weight space, this gives us an isomorphism on the weight spaces, and it has this more manageable and friendly expression. And here, when I write F parentheses K, these are the divided powers of E and F. So this is F to the K divided by K factorial. So this is an interesting element whose action we can look at on the Lie algebra level. And so this has also been considered on the categorical level. So here, now we are going to consider a complex of functors, theta, where each of the theta n's itself is a functor from the category of complexes from C minus n to complexes on Cn, where remember C minus n and Cn are corresponding to the weight spaces for any given representation. And so here's what it looks like without too much detail. So it's a complex of functors. So the way it works is you apply it to a complex with whose terms are objects in this category C minus n, you get a double complex, and taking the total complex of that, you get then a complex on Cn. And here, the functors E parentheses n and F parentheses n are categorifying the divided powers of E and F, and they are obtained using the Nilaffa and Hecke algebra action. And the differential in this complex comes from the natural transformations that we have in the structure. So in particular, the adjunction units and co-units and so on. So this is the categorical version of the Rickard complex. And so then one of the results of Chuang and Rouquier tells us that this complex then induces derived equivalence on the bounded derived category of our G categorical representation C. So in this way, these Rickard complexes are giving us some information about the symmetries of these derived categories. And in particular, if we restrict it to the weight categories, then we get an equivalence there as well. And the decategorification of this complex is the element S that we were looking at. Okay, so So then an example, again, in the SL2 case is still considering the adjoint representation. Let's just focus on the zero weight space. So looking at this equivalence when n equals to 0, then remember that the categorification we saw earlier had C0 being modules over this ring, and this theta 0 is given by, so for any R module, it maps it to the complex R tensor n to n, where n here is in homological degree 0, and the map is given by the action of R on n. So this is one example of this Rickard complex. And so we're interested in understanding further the structure of these Rickard complexes. And in particular, we would like to show that they're what is known as perverse equivalences. So here's a little bit, perhaps, scary definition, but let me go through it with you. So suppose we have, so as in our setting, 2 abelian categories and an equivalence between their bounded derived categories. And furthermore, let's assume that these categories A and A prime are filtered by Serre subcategories, and we also have a certain perversity function from the indexing set of the filtration to the integers. Then we say that this equivalence is perverse with respect to this information if it satisfies the following two properties. So, let me perhaps mention that, so these bounded derived categories are in particular triangulated, and so we have a shift functor. So here, f shifted by an integer given by the perversity function, we want that to restrict to an equivalence of the following form, where db sub ai of a is so a fixed subcategory of the original derived category of the complexes whose cohomology lives in ai, where ai is given by the filtration. So we want f to restrict to an equivalence on these fixed subcategories. And so we also get an equivalence on their quotients. And so we want that also to induce an equivalence on the quotients of the original Serre subcategories of our abelian categories. So maybe a more intuitive way to think about it is, let me say this, it might make it better or worse to understand, but suppose we have so an equivalence on triangulated categories, which in this case is what these bounded derived categories are. And suppose that both of them are filtered by fixed subcategories, and that this equivalence is compatible with the filtration. Then we say that it's perverse if on each of the composition factors of the filtration, it is T exact up to shift using the T structure on these triangulated categories. So, and this shift, which we have to apply to get T exactness, might depend on which composition factor we're working with. This is a certain further nice property we can hope that such an equivalence will have. And so let me go on and tell you further how this relates to the Rickard complexes. So here's an example again in the case of SL2, where, so suppose C is a category endowed with an SL2 categorical action. And now let's look at its set of simple objects, where one of the conditions I had omitted mentioning before, but perhaps is worth mentioning here, is that we want the objects to have finite composition series. So given the set of simple objects S, we can define the filtration in terms of the simple objects. And then this gives us a filtration on C by taking the Serre subcategories generated by these sets of simple objects. So in this case, the filtrations are given by, so two different filtrations, by what powers of F or E respectively of the F and E functors are killing the simple object V. And if we also take the perversity function to be the identity, then a result by Chuang and Rouquier tells us that with this information, the Rickard complex is perverse. Okay. So let's now talk a little bit more generally in the case of a general Kac-Moody the algebra G. Oops, sorry. So for a general G, so remember in the case of SL2, we just had a single non-trivial element of the Weyl group, which I called S. But here we can have a more general Weyl group element, and we take a reduced word for it. And we're also going to fix a weight for the G representation we're working with. And then we can consider the composition. So for each of the Weyl group generators in the reduced word, compose the corresponding Rickard complexes, so define them the same way we saw earlier. And so the theorem, which is slightly out of focus, which we are in the process of writing up, says that if you take the longest element of the Weyl group and a weight for the given representation we're working with, then maybe I can, oops, sorry. Maybe this is a little bit more visible. So here, the corresponding Rickard complex is going to be a perverse equivalence. I haven't told you here what the filtrations and the perversity function have to be, but in this case, the filtrations are related to the isotypic components for the representation, and the perversity function is related to the shift in the T exactness that I mentioned in the definition of perverse equivalences. So for the sake of finishing on time, I will not get into the details of that. Let me just go back to the full, okay. So in the, so now that we have these perverse equivalences given by the Rickard functors, let me say how we relate them to the actions of the braid group and the cactus group that we saw earlier. So, okay, I'll just go this way. So for our Kac-Moody algebra G, we can define a braid group, the corresponding braid group, which is generated by elements indexed by I, where I here is the Dynkin diagram of G. And we have the following relations. So sigma I, sigma j, sigma I, sigma j, sigma I, sigma j, if I and j are connected in the Dynkin diagram, and any two elements commute whenever I and j are not connected in the Dynkin diagram. And sorry, I'll just go to the next slide here. And we also have a cousin of this braid group, which is the cactus group, which is now generated by elements indexed by connected subdiagrams of the Dynkin diagram. So again, we can obtain this or define it using the Dynkin diagram, and they have several relations. In particular, each of these elements is an involution. Maybe I won't get into details of what all the relations are, but it's very explicit. And so in work of Cautis Kamnitzer, we can see that the Rickard complexes satisfy the braid relations. And so they in particular give us a categorical braid group action. And so now I'm going to my last slide. So, whoops, sorry. So going back to this picture, we have the Rickard complexes giving us a braid group action. But since they're perverse equivalences, in particular, we also know that they induce a bijection on the underlying, on the simple objects of the underlying category. So for the Rickard complex indexed by the longest Weyl group element for the sublinking diagram J, the bijection it induces on simple objects I'll call theta J. And then we show that the map going from taking an element of the cactus group to this theta J defines a cactus group action. And so we get from the Rickard complexes, we retrieve back the cactus group action on a single crystal where the simple objects of this category have structure of a crystal as described by Lauda and Vazirani. So, okay, I'll stop here, out of time.